these equations seem somewhat like we're just forcing solution templates, but it turns out that homogeneous systems do arise in the real world actually pretty often. But let's consider a tank problem where the inflow and outflow rates of water are not the same. So therefore, internal volume is changing. So let's consider this particular problem. Instead of using a tank, we'll say we have an oil refinery, and this, well, like I said, is a tank. A storage tank contains 2,000 gallons of gasoline that initially has 100 pounds of an additive dissolved in it. In preparation for winter weather, gasoline containing 2 pounds of additive per gallon is pumped into the tank at a rate of 40 gallons per minute. The well-mixed solution is pumped out at a rate of 45 gallons per minute. How much of the additive is in the tank 20 minutes after the pumping process begins? Okay, so we clearly want to keep track of the amount of additive in there. We have oil in here. We're adding 2 pounds per gallon of this additive, and the mixture is coming out at 40 gallons per minute. This mixture is that of gasoline and the additive, and so it becomes well mixed inside of this tank and then flows out the bottom at 45 gallons per minute, and we are now going to build that expression. So we're going to define our variables. So y equals the amount of the additive in tank after, we'll say this is in minutes, t minutes. This also saves us from having to define t separately. We could just say after t minutes, and now we know exactly what that represents. Now this additive is going to be measured in pounds. T is measured in minutes. I'll just go ahead and write it out anyway. Minutes since additive begins entering tank. Okay, and so that means dy dt, as we like to establish, what are the meanings of our units? Well, this is going to be in pounds over minutes. So that's our units. Now what we have coming in is, we already said it's 40 gallons per 1 minute, but 2 pounds are added to every 1 gallon of this additive. So every minute we have 80 pounds of the additive coming in. So 80 pounds per 1 minute. And already that gives me the inflow term. That tells me that this is going to be 80 pounds per minute. That's already in the correct units. Now I'll have a minus term here because I also have my outflow. And on my outflow side, I actually have to think about the fact that I have 45 gallons per 1 minute coming out, multiplied by how much is inside of that tank. Well, I know that there are y pounds inside of that tank at any moment, and I know that initially this contains 2,000 gallons. So I know that in terms of my units here, in terms of pounds over gallons, I have y pounds inside of that tank at any moment. But the problem is I don't have 2,000 gallons at all times. Let's think about this intuitively, what's going to happen in terms of my volume. We'll just refer to that as V for a second. So if we look at the time and we look at the volume inside of this, so we have V gallons, but we don't just want to put a V there because, well, that's a third variable. We have y, v, and t. Now, we know that v is actually going to change depending on time passing. Well, at time 0, we know that we have 2,000 gallons. Now, over the course of 1 minute, let's think about what happens. We have the 2,000 gallons from the previous minute. We've added 40 gallons from what came in, but we've removed 45 gallons from what came out. So in actuality, what we did is we removed 5 gallons in net of the total amount of mixed gasoline in there. So we actually only have 1,995 gallons remaining. Okay, so time 2, you can imagine again what's going to happen is now we start off with 1,995. We add 40, but we subtract 45. So plus 40 minus 45 is going to give me 1,990. So we can see here that basically this is a linear function, that the volume is decreasing linearly. And so for time t in general, we would have the original 2,000 gallons from the top minus 5 gallons per minute that are leaving the tank multiplied by how many minutes have passed. So if we do a dimensional analysis on this, what we should notice is that this is gallons minus, this is how many gallons per minute we're losing, multiplied by how many minutes. So in terms of our units, we get gallons minus gallons. So this V of t we just found equals 2,000 minus 5t. So my dy dt, oops, this is not my dy dt. My dy dt is down here, is going to be, this is going to be 45 gallons per 1 minute multiplied by y pounds per 2,000 minus 5t gallons. And that's going to give me the units I need. So now my final equation is 45y over 2,000 minus 5t. And there is that model. Now it might not be immediately evident, but this is a first order linear differential equation. So this is our model right here. And we also know the initial condition. The initial condition is, well, let's see, initially has 100 pounds of an additive, so this means that y of 0 is equal to 100 pounds. And we're ready to solve this differential equation, and in order to do that, we want to say, is this separable? And it's not, because notice that this term contains a t, but this term does not. So it's not as if I could factor this into one term containing t and one term not containing t. If I factor out 1 over 2,000 minus 5t and pull it out front, I'm going to have to factor that out of an 80 as well. So that means I'm going to have to divide by 1 over 2,000 minus 5t, if I do it that way. Let me go ahead and write the y term first, and let me also separate the y from everything else. So if I write this as negative 45 over 2,000 minus 5t times y, which is just me factoring out all of this right here, factoring all of that out, now I can see that this is going to be my a of t. And then I have a positive 80 here that I can put on the end. And so now when I look at the general form of a first order linear differential equation, we can see that we have a perfect match for our method. So we have, first of all, we have that this is a of t, and we have that 80 is our b of t. Now if this were a minus, by the way, we would have to write this as plus negative 80, just a little FYI for the future. We're ready to solve. So to solve, step 1, we have to calculate mu, and I'll just write it as mu. You can write mu of t, e to the negative integral of a of t dt, which equals e to the negative integral of negative 45 over 2,000 minus 5t dt. Again, we just have to focus on that integral right there. So let's go ahead and type that into Wolfram Alpha. By the way, the two negatives cancel each other out, so I'll just write the integral of 45 over 2,000 minus 5t. 45 over 2,000 minus 5t, and that's going to be all dt. So let's just make sure that looks correct the way we wanted it to be entered in. And something seems to have caused this a problem. Let's see, it might be this. Yeah, it might be that needs to be in the exponent. And that looks right. E to the integral of 45 over 2000 minus 5t comes out to 1 over t minus 400 to the ninth. Now the beautiful part here is that Wolfram Alpha simplifies everything for us, so we get to focus more on the solving of the differential equation instead of having to worry about doing the integration in addition to everything else. So there we go. So we have that integral written out now. That equals 1 over t minus 400 to the ninth. Okay, so that means step 2 is to find the general solution, 1 over mu times the integral of mu times b dt. I'm not really sure why I'm not putting mu of t, and I am doing it on the b of t, but here, just to be consistent, we'll remove that. All right, 1 over mu, so we have, this is 1 over t minus 400 to the ninth, and multiplied by 1 over t minus 400 to the ninth, multiplied by our b of t. Recall our b of t is 80, so that just impacts this by a constant. And now we're ready to compute this integral. The one thing that I will point out is that this is 1 over, which will just be t minus 400 to the ninth. And the integral of this, and that integral comes out to this ugly looking expression here, negative 10 over t minus 400 to the 8th. Oh, that's not so bad. And then we have plus our arbitrary constant. All right, so now when we distribute this in, we have to be cautious to make sure we distribute into both terms within the parentheses. And the first term we see will have t minus 400 to the ninth over t minus 400 to the 8th. And so the power of 9 and the power of 8 will cancel, and we'll just be left with negative t times t minus 400 to the first. So that 9 minus 8 is 1, and the 1 will end up in the numerator. Plus c times t minus 400 to the ninth. And here is our general solution. So now for our initial condition, we said initially there are 100 pounds at time 0, and 0 minus 400 here to the ninth power. And this gives me 100 equals, this will be 4,000 plus, or I should say rather minus, oh, we could write it like this, negative 400 to the ninth times c. So negative 400 to the ninth, c times that. Now I'm not actually going to try to calculate this in my calculator because negative 400 to the ninth power is going to be a very sizable number. So to write that out is asking for some trouble, to write out too many decimal places. So I'm just going to leave it like that. And this might be a new thing that you're seeing here, order of magnitude. Order of magnitude here is very large. So it's sometimes when you have magnitudes that large, it's better just to keep things in exact form. So subtract over 4,000, so give us negative 3,900 equals negative 400 to the ninth times c. And so c is, by the way, since this is to an odd power, this is going to end up being a negative number. So I can't actually make this negative come out here. If this were an even power, then raising a negative number to an even power would produce a positive number. And you can just check my logic on that if you'd like. So this will be 3,900 over 400 to the ninth power. Now this is very small, very, very small. In fact, it's approximately 0. So it might be tempting to just say, well, since it's pretty much 0, let's just leave it as 0. But I will say, do not round to 0. The reason we don't want to round to 0 is because the value of c basically activates this second term. So even though this c value may be extremely small. Here we have t minus 400 to the 9th power. So even when this is really small, and t is, say, 1, 2, 3, 4, 5, well, this number here raised to the 9th power is going to be incredibly large. And if c is really small, but what it's multiplying is incredibly large, this term could still be highly significant, even for a small coefficient. So one thing to be cautious of, do not round things off to 0. Do not round arbitrary constants off to 0. So our final solution is y equals negative 10. If I distribute this out, which I can do, actually, let me do a couple of things here. C times, so I'll write this term first, C, which is 3900 over 400 to the 9th, times t minus 400 to the 9th. That's just me writing out this term here with c in its place. And then I'll distribute this negative 10 through and make this negative 10t plus 4,000. And I'll leave that right there as my final solution. Now the question we wanted to know is how much will be in there after 20 minutes. So we want to estimate y of 20. Now I'm going to go ahead and type this into decimals just to demonstrate why it's so important that we kept that c value. So far I've entered that equation in, and here's what's happening. Very interesting stuff. Actually, one of the things that we should note, and it appears here that this is time in minutes, and this is the additive in pounds. And we see that at some point the additive actually becomes negative, that the amount of additive in the gas tank, the additive is increasing over time until it peaks at around 95 minutes, and a total of 2,710 pounds of that additive, but then the amount of additive begins to go down. And that is sort of a curious issue here, but let's go ahead and handle one battle at a time here. Let's go up to time 500. So now we're focusing more on the important piece of the graph. Now the one thing that I wanted to point out is if I took this away and made this 0, look at how drastically that changed the solution. Look at how drastically our solution changed. It looks like the additive, first of all, starts at 4,000, and it doesn't. It starts at 100. And whoops, this was 3,900 over 400 to the 9th power. So now you can see that here our initial condition is satisfied, and that tiny constant, which by the way, if you estimate that, comes out to something times 10 to the negative 20. So there's 19 decimal places before the first non-zero number. That's why we left it that way. Now I wanted to estimate how much is left after 20 minutes, and it's 1,347.0 total pounds. Now, another thing I could do here is just type in the ordered pair so I can actually see that on the graph. So there you can see it. That's how much is present after 20 minutes. Now, the one thing that we have to remember is the volume of the tank is decreasing, right? So the volume as a function of x, I'll call this the volume function, is 2,000 minus 5x. So that volume function, if you take a look at a table of values for your volume, and we look at the volume over, let's say, time 0, there's 2,000 gallons. Time 10, there's only 1,950. Time 20, time 30, time 40, you can see that the amount of gasoline inside of the tank is decreasing. So if we went to 200, 300, 400, 500, 600, you can see that at time 400, 400 times 5 is 2,000. 2,000 minus 2,000 is 0. So this is the time, you can see that this is the volume function. The volume inside of that tank is decreasing, and at time 400, we run out of gasoline. And that's why there's no more additive, because additive comes in with the gasoline, and since everything's being drained, then there's nothing inside of the tank. So at some point we max out, reason being because we're still adding more additive than there was, but now the effect of the decreasing volume is causing the amount of additive, the net amount of additive in that tank to go down as well. So that's pretty much it. We can see those are some of the key features of this graph. And with that, you can see that we had a very natural application that ended up giving us a non-homogeneous first order linear differential equation that we had to solve now using our method. We could, of course, have done this using the extended linearity principle. The challenge with that would be to come up with our guess. That function of time here makes it really tricky to do this. When we were dealing with the extended linearity principle, our coefficients here were constants. And because they were constants, it made it easy to form that guess. But since this function may not be a constant, as it isn't here, it makes a lot more sense for us to have derived this general solution method.